the topic of what I want to do today. So I'll go over again kind of quickly what I did at the last time, which was about this this internal symmetry, the theory that if you write down either a pair of scalar fields or a complex scalar field and satisfying the Klein-Gordon equation and do quantize it the way we've been talking about, that you end up with a theory that's doesn't just have the Poincare group and the Poincare Lie algebra acting on it through quadratic operators, but there's also a quadratic charge operator, which has integer eigenvalues, and it corresponds to the kind of symmetry of multiplying this kind of complex value of the scalar field by a phase by e to the I theta. So let me kind of quickly say that again, and there's a couple confusing things about that, and then we'll get on to the main topic of today, which is I want to tell you about gauge symmetry and about how to. But anyway, what happens when you so-called gauge the symmetry, and we'll get started on what we'll be doing for the next week or so. We're talking about electromagnetism and how to quantize how to couple quantum fields to the electromagnetic field and how to quantize the electromagnetic field. Okay, so let's see. So what so last time what I was doing was I was saying that what I did is really you consider a pair of real scalar fields. And then what you get, so you can write these down as, I don't know, phi1. And then you look at, say, well, we're going to quantize the space of solutions, the Klein-Gordon equation, and the Klein-Gordon equation doesn't do anything with this index. It's just two copies of the standard Klein-Gordon equation. And then what I said last time is that if you do this, what you find is that let's see. So you can define. Call it Q hat. And I've got an I integral of R3, 3A2 dagger of theta. Vector. And then So maybe it's, I guess, easiest to see what's going on as usual in the momentum space, where you've kind of decoupled your theory is really just a bunch of decoupled harmonic oscillators, one for each element of each momentum. So what you've got here is, and so if you want, I can also multiply this by I could also say that this guy is, so I've put the I here in order to make this a self-adjoint operator. So in order to make this thing have real eigenvalues, but you can anyway. So you can calculate. Well, let me anyway. I'm not actually gonna. So anyway, you can calculate what this operator does, how this operator infinitesimally acts on phi1 and phi2, and really what this is he's really just the thing that in the infinitesimal action of this guy. If you commute this guy with phi1, you're going to get plus or minus phi2. If you commute it with phi2, you're going to get plus or minus phi1. So this is basically, this is just the Lie algebra operator that generates rotations, that generates rotations in the plane, in the 1-2 plane. So now so this is kind of, and you can anyway, and then you found also that the Hamiltonian was just the integral over R cubed of omega p. Of p. So it's just this is really just, as far as the Hamiltonian is concerned, and as far as dynamics is concerned, it's really just two independent copies of the scalar field theory. Okay, so but what I want to do is so what I'd like to do is actually change variables so that this guy is diagonalized, so that this guy he's going to have eigenvalues plus or minus 1 on acting on the space of these things. And the problem with working with two real scalar fields is that they're not they're not eigenvectors for the symmetry generated by this thing. So you want to take phi 1 plus or minus I phi 2, and that will give you the eigenvectors for this guy that have these are going to be things that have a well-defined charge. So if you think of it physically, these phi 1 and phi 2, they create standard scalar fields that are particles which are their own antiparticles, but they don't have any fixed. You have this operator which kind of mixes them, but these don't have any kind of phi 1 or phi 2 don't have a fixed property under Q. They're not there is no eigenvalue of Q. Just that if you're just acting on these, you have to somehow put them together to get eigenvectors. And so what you do, maybe one way there are a lot of ways of motivating this. But what I do is define. So you define new complex linear combinations of these things which diagonalize the action of this guy. So you define A of p. What did I do? 1 over square root 2. A1 of p plus I and then B of p. Okay, so you define these combinations, and then what you then expressed in terms of these guys, then Q is the integral if you write this there, if we write this thing in terms of these variables, you get this. So this now is something that makes a lot more. Now we've kind of separated out the degrees of freedom in a way that makes more sense, for this observable. So what this is saying is that and then what you so what this is saying is that you've got that you're basically the charge operator basically for each value of p is the number operator. It counts the number of quanta you have of the number of kind of A-type quanta you have at a given time, and then it subtracts the number of B quanta that you have. So this is kind of particle number. And this is anti-particle number. Okay. So these variables. So these guys are all set. So part of making all this work is we also have to define the vacuum state as the thing that this is 0 and B. This is and anyway, so this is just the usual thing with the harmonic oscillators. We have to make sure that our state space is such that you know, the number of eigenvalues go. It has a lowest zero number eigenvalue, and then the number of eigenvalues go up are positive. So you don't have negative numbers of things. But anyway, this is the so the physical interpretation is that this is just counting up to, you know, that you've got A kinds of particles and B kinds of particles, and they have the same behavior, except that they have opposite behavior under this and this charge operator. But these things, you would say, have charge 1, you get 1 for each extra particle quantum, and you get -1 for each antiparticle quantum. Okay, so that's the general story. I mean, there's various other ways of thinking about it, which I put in there. I'm not sure that this is probably about as simple as you can make it. This is kind of a general thing about quantum field theories in general. That if you have real scalar fields, then they don't kind of come with any inherent notion of charge. If you want to talk about charged fields, what you typically do is you typically complexify and work with complex linear combinations and play this trick. So that's the. I'm trying to think if there's more to. Yeah, I won't kind of. I mean, you can also then. So in the book, I also then wrote, worked out in a lot more detail exactly what the. Okay, maybe I should say that. Say something about that. So in X space, so if you Fourier transform to X space, then your basic variables you're working with are these phi's and pi's, and then you have so you have phi. Let's see, let me call this phi hat. Phi hat dagger. Phi. So remember, so what happened in the real scalar field case that you really just had these. You didn't have this and you didn't have this. You just had phi and pi. They were those were the only operators you had. These all depend on X. And but now in this for this theory with antiparticles, you actually have two kinds of things. You have things and their adjoints that are not the same. Or you can think of it as being in the real case. You can think of this as the general story, and then in the real case, you impose a condition that phi is equal to its adjoint and pi is equal to its adjoint. You do it either way. Anyway, but you can then go down and you can write the expression for Q in terms of these fields. You can write the Hamiltonian in terms of these fields and everything. And I think I won't go through that. But if you want to see some more details of how the story works out, that there are anyway. There's also various choices in how. So you can think of this as really. This as a quantization of a complex valued cells B. And then you have phi, the X vector, and phi bar. So if you want, you can kind of go back to and work kind of classically with take your phase space. Well, now the coordinates in this phase space are now complex, and what gets confusing when you do this though is that in order to do this, in order to do the quantum field theory quantization, and you want to choose do Bargmann-Fock by choosing a complex structure that breaks things up into positive and negative energy. Well, here you've got a different complex structure, which is just the complex structure coming from the fact that phi takes complex values. So there's, if you try and think about your phase space, you know, your phase space M as being these guys, you know, these guys, and I guess you would also need to also pi and pi bar. If you take these as coordinates on your phase space, then the problem is that you really want to. So the problem, in some sense, is that what you're supposed to do is take M and complexify it, but you're complexifying it over the reals. So you have, anyway. So what you mean by complexification then becomes very confusing, because you're when you complexify something, it's already complex. But so I don't want to. I don't want to belabor this. Mainly just to point out that if you actually look in look at wherever you look in a quantum field theory textbook about quantization of a complex scalar field, something funny has to go on. That there's kind of there's really two complex structures floating around. The usual one from just taking complex values, and the one from that you need to do Bargmann-Fock, which is the decomposition of positive and negative energy. Okay, I think maybe that's enough to say about that. So, are there any questions about this? Okay, if not, so let me move on to the next thing, which is maybe a lot more interesting. Okay, so what you have here is you have kind of an extra symmetry of the theory, which is this overall U1 group acting, and going back to the beginning of the course, the fact that you've got a U1 group acting just means that your states are can be decomposed into irreducible representations of the U1, so you can associate integers. You can associate an integer charge to any state, any of your states. You can break them up so that they're charge eigenvectors. But what we're going to do now is actually use this charge. So the thing about this about electric charge is that it's really the fundamental object which determines, for elementary particles, the way in which they kind of interact with each other. And what's actually happening is that, as far as we know, if you're talking about electrons or electrons, the way two electrons actually affect each other is they don't affect each other directly. There's no kind of extra self-interaction term in the Hamiltonian for electrons. But what there is that this fact that they have this charge is that they can actually couple to a background electromagnetic field. So what we want to do today is want to couple the charge of field of phi to a background electromagnetic field. So this is mainly what I want to discuss today. And so the theory that we're going to get is going to be it's going to describe physically a kind of fixed electric and magnetic field in the background, and then a quantum field theory of multiple particles which are interacting with that fixed background. And so I'll explain that as we go on. And then next time, what we're going to do, the next part of the story that we'll get onto next time is how to actually quantize the electromagnetic field. To think of the electromagnetic field as something that you should actually quantize also. But for today, this electromagnetic field is just going to be a fixed background. So what I want to kind of motivate this, like everything that I've been doing in this course, you can kind of motivate this whole story. How you're going to define this electromagnetic field and how you're going to couple to it using a notion of symmetry. And so what we're going to do is the new notion of symmetry is something we'll call gauge symmetry. And the basic idea is that we had so far what I've been talking to you about so far was a the charge was coming from this overall U1 gauge symmetry, that there was a group U1 that was acting by phase rotations uniformly on the fields everywhere. So that's what's called a global symmetry. But so what we want to do is have the U1 act on the field independently at each so at each point in space and time, you're going to have a U1 group acting on the field values, but it's not. It's going to be different. It's going to act differently at different points in space and time. And so here, I guess I gave you this is that now. So what you're doing when you do this is you're defining a new group, and you're defining a group which is a copy of U1 for each value of at every point in space and time, and you're and this is called the gauge group. So let me define it. And so this is called, I guess I'll define this is what I'll be calling the gauge group. And notice that what I'm doing here, everything depends upon having this specific group to start with, this U1 group. So later we'll ask what happens if you change that. But for now, there's always a U1 group. And so the gauge group is the group of functions, what I call it, on Minkowski space, values in U of 1. So an element will be so you can write them. So you write it as e to the I, I want to take 5x. So I mean, what you want to do when you write this thing down is that these group elements are kind of nonlinear. They live in a circle. So you want to kind of unwind the circle and kind of think of your group elements as so 5x. Actually, do I want to? Yeah. Okay. To make this to make this a little bit more complicated, I'm gonna. At some point in the story, you have to put in a normalization, a constant, which everybody's normalization depends on. You can put it in various places. I'm going to put it here. X. So E is a constant. It's going to end up determining the strength of the electromagnetic, of the coupling between the charged particle to this background field. So 5x is a real number, but in some sense, you're identifying it. It only depends upon 2 pi z. That if you change 5x by some number of some overall 2 pi's, you're going to get the same thing. And so
I guess there's a reason it's called E.
Yeah. It's electric charge, yeah.
Yeah, okay.
Okay, yeah. So that's what it's going to be, and yeah. So I think when I actually wrote this chapter, I actually at various times changed the places where I put the E. I thought, anyway. So if you don't put it here, it's going to appear later in a place that I liked even less than having it appear here. So, but it's another way of saying it is that your E really, some sense, knows about how you normalize phi and how you relate. Actually, sorry, I guess I've also done something funny here. That is, sorry, this is 2 pi Z times E, I guess, over E, right? Over E. Yeah. So you have to watch. Anyway, it kind of shows up, affects everything, but it's really just a number and just a normalization. Which you, in some sense, you've got to keep track of how you're normalizing your Lie algebra. So these are kind of a, these are group elements at each point, and these are Lie algebra elements, and how you've decided to normalize this, your notion of the size of things in this Lie algebra depends upon this E, and you have to put it somewhere. Okay, and then the group law. So you have e to the, so if you have two of these functions, e to the I e phi 1 of x, and you can multiply it by another one in the obvious way. One of x plus. Okay. So I mean, it's just pointwise multiplication of these things. So the thing about gauge symmetry is it's very much an internal symmetry. It really doesn't know anything about the Poincare group, or about, it doesn't in any way relate different points in space-time. It just tells you, it just affects the values of the field at a given point in at a given point at each point in space-time, and it does it just completely independently. Anyway, so when somebody says the gauge group, what they often mean is the functions. It's a group of functions on M4 valued in U1, and explicitly you'll often think of it in terms of these phi functions this way. But the thing, okay, now the thing to say about this is, notice, maybe, well, okay, maybe let me just say this is a problem. So one's initial reaction to this might be, okay, great, I've learned all this stuff about representation theory of groups. This is a Lie group, so I just now, what are its representations? Let's start using representation theory. Well, the problem with this, is that the gauge group is infinite dimensional. So everything that we've done so far with well, I mean, I guess it's not quite true that in some sense we've already seen an infinite dimensional Lie group, which is when we do canonical quantization of a quantum field theory, then we're basically using a Heisenberg Lie algebra and a Heisenberg Lie group, which is infinite dimensional. And actually, in some sense, if you anyway, so there actually is some relationship to that, but maybe I better not get into that. But anyway, the basic problem here is that you don't know. So we don't know what the right notion of unitary representation is. So it's an infinite dimensional group, and you have to figure out what kind of representations are you going to allow, and there's a long story, but it turns out for the things that the basic things I'm going to be talking about is that we only care about the trivial representation. So the idea most of the time, generally what we're going to do is that we're going to say, well, there's this infinite dimensional group running around, which acts on all the fields and everything. But it turns out that instead of saying we want to decompose the physical Hilbert space into unitary representations of this group, what we want to do is we want to say that the physical Hilbert space of H will be invariant under this group. And there's actually a lot more to say about it, but maybe just to keep things simple, maybe that's the thing that you should think about for now, is that I've introduced this new group. It's infinite dimensional. You'd like to think about its representation theory, but I have to warn you that if you try and do that, it's going to be hard. But what we really, the standard story that we're going to tell is that it is really all based upon on setting up a theory and a state space that's just invariant under the action of this group. So the only interesting representation, in some sense, is supposed to be the trivial representation. So this is the general story of kind of gauge symmetry, though there's a lot more to it. Okay, so now what are we going to do? So the more interesting thing about this. Okay. So this, and I guess I'll give this a name. I guess I sometimes call it a curly G. And so then G, curly G, acts on complex fields by what? So psi of x. Now I'll change for no particular good reason here. I guess I'll change. Actually, maybe. I guess it's well. For no particular reason, I'm using psi instead of phi here. But and anyway, so this is x is space and time. What is it? E to the I, e phi of x, and psi bar x. Oppositely, the group x by e to the minus I. So this is just saying what I was saying. The whole kind of motivating idea of this thing is that this is something that if you took this phi to be space-time independent, so it didn't depend on x, then you would be back to the story that I was starting off with today, so-called global U1 symmetry. But now, so the only difference is we're allowing kind of x dependence in this U1 phase factor. Okay, so now the problem was, okay, so our problem is that the Hamiltonian, or the problem with this written the way it is that if you just try the standard Hamiltonian, so the usual Hamiltonian is not invariant. So if you did a global U1 changes, and if you looked at the formulas you had for the Hamiltonian, either in these A and A daggers or these psi and phi and psi of x, that they if you multiplied the terms would have an equal number of psis and psi bars in them, or of A and A daggers, so that if you did a global phase change on everything, that the Hamiltonian wouldn't change. But the problem with the Hamiltonian is that the Hamiltonian has derivative terms in it, and the derivatives are going to cause trouble because of the x dependence of these things. So the problem is that, well, there are various ways of writing the Hamiltonian, but you have, for instance, if you have that phi terms are not G invariant. Okay, so if you do a gauge transformation on a term like this, you're going to have, it's going to turn into something quite a bit more complicated, and you're not, this gauge symmetry is definitely not going to commute, is not going to commute with the Hamiltonian. It's not going to, and you've got a mess. So it turns out the way to fix this, okay, and actually I guess I calculated this thing here. So I said that, so d phi dx of x, if you make that change, what you get is you get a what you end up with is you end up with, if you make this change, you end up with an e to the pi e5x times an IE x, there's mu here, for a plus d dx view. Anyway, if you just calculate what happens to this derivative as I do this, you end up with there's one term, the term ignoring this, where the phase factor just goes out of the derivative, and then if you put it in here, it would just cancel. But your problem is this term. This is the term that's going to mess things up. Okay, and it comes from the fact that you can if phi can be x dependent. If phi were a constant, you wouldn't have this term, and then you would say that your derivatives, we often say that your derivatives behave covariantly. Derivatives behave the same way as the phi's, and so you can just create terms like this, and they're invariant. But the problem is this guy. Okay, so there's not at all obvious way of dealing with this problem, which is this. So the idea is to introduce just a new kind of field. And so we'll call this, let me call it, so it's going to be something that depends upon where you are in space-time, but it also carries a space-time index. So mu is equal to 0, 1, 2, 3. So this thing, or you can think of it this way: it's got a piece which is mu is equal to 0. It's got a function a0 that depends upon where you are in time and space, and it's got 3. Maybe let me just put it here. It's kind of a spatial vector valued thing that depends upon where you are in space. So we're going to introduce this guy, and then the plan is to make that this guy behave in a way under gauge transformations that we can use him to cancel this problem. That's what this. And the okay, so the names for this thing, and so this is called the vector potential. So that's more of a standard physics terminology for this guy. Or mathematicians often say that, well, this is a connection. This is a connection. So anyway, these are just two different languages for the same thing, but it's this guy. And what you want to do such that with G acting by. So this is also going to not be invariant under gauge transformations, but it's going to be by mu of t x vector goes to, and so sometimes what I'll do is I'll write the so-called gauge transform version of a field by putting the phi that's used to transform it up there, and that's so the x vector. And what it is it's the it's a mu of t and x vector. It's the same thing, but then but plus an extra term plus d phi of t x. And now, okay, yeah, that's right. So so the idea is that we're going to use this behavior under time, under spatially changing gauge transformations to cancel this guy. And so what we do is you then define. I'll get rid of this. Define. And you say that the covariant given a connection so I'll write it I'll often just write it just with an A to mean this gadget. You have the associated covariant derivative is, and then the A. So it's kind of it's going to be a replacement for a usual derivative, and it's going to have the direction you're differentiating in, but we're going to use a big D instead of a curly D, and put an A to say what the connection is. But it's just going to be the usual derivative and then minus I E A mu. Okay. So this is called the covariant derivative, and the general kind of philosophy so there's going to be a lot of geometry behind this, which I'll try to say something about as we go on. But the general, what you'll also see when mathematicians are working with these things is that they'll often kind of identify. The whole point of this A is that it gives you a new kind of derivative, and so they'll when people are talking about connections, they'll often just kind of identify, more or less identify the connections and the associated covariant derivatives. So any theory that you write down by writing down properties of the A's, you can also write down by writing down properties of these operators. But the whole point of this is that you can do this calculation that if you take E mu A so if you take this new kind of derivative of this guy, and well, let me anyway, and so then you gauge transform the psi by multiplying by e to the I e psi of x, and you gauge transform the a mu by doing this. Then what you'll find is you find that the this guy under this gauge transformation goes to, there's an e to the I e psi of x. There's no, and then that gets multiplied by the original thing. And then you're going to have two terms. You're going to have the term from that thing I erased. There's an IE dx mu, and then there's a minus. Mu. Psi x. so the point is going to be that when you change this way, you pick up this term here, and it's going to cancel the problematic term that you had in the calculation before. So these two terms are going to cancel, and you end up with just e to the I e of x e a. Okay. So the whole point of this covariant derivative is to make derivatives behave, if you like, covariantly, to behave in the nice way that derivatives behaved when you didn't have x dependence. And so now what you do is just replace so now what you do is just to couple. Well, let's do this right. So to make the Klein-Gordon theory gauge invariant, what you just do, all that you do is you just replace replace in your Hamiltonian d psi d phi phi u a phi. So basically, wherever you had a standard derivative in your dynamics, in your standard derivative, you just change it to a covariant derivative. And then what you're going to do, what this is going to do is you have your underlying theory now has this infinite dimensional group of symmetries, but it is doing something funny. But you've actually coupled the theory to a completely new degree of freedom. So you have infinite dimensional gauge symmetry. But with and the theory is invariant under G. So your space of states are now supposed to not depend upon G, but and also you have a new degree of freedom. You have new fields. In u of x. So you've managed to make this theory invariant under this infinite dimensional group and this group of gauge symmetry, but you've done it by adding in by changing the terms in the dynamics to new terms which involve this different field A, which is also a field that depends upon
how would you determine the A?
What?
How would you determine the A?
Okay, yeah. So right now, so for now, yeah. For now, we just pick an A, pick an A, and it doesn't and you're picking a mu of x. So you just pick some function like this, and what's going to happen is that you then couple, then write down G theory with d mu A, and what's the physical interpretation is going to be a theory of scalar fields coupled to a background electromagnetic field. So it turns out, I mean, what turns out to happen is that these fields are exactly, these fields, these so-called vector potential and connection fields, are exactly the right thing to describe some kind of background electric and magnetic field, which, if you had a charged particle, the way it interacts with this these background electromagnetic fields would be determined exactly by these terms. Okay. So let me. Okay.
Quick question.
Yeah.
So how do you know, or maybe you don't know, does this preserve all the other symmetries?
No, yeah. So note, yeah, good thing to note, in that in general this breaks. Breaks Poincare in general. Yeah. So the whole point of this is you have this kind of, you've introduced this new degree of freedom, which is not invariant under, which does different things at different space times. It's not yet. So you no longer have a So what you should, I'll write some of this down in a minute more, but you should think of this as really what you've done is you've just picked you've made some kind of choice of some weird electric and magnetic field, which is fixed, which is not doing anything. It's just sitting there. Maybe it's a solution of, well, anyway, let's just pick, it's just some fixed electric and magnetic field, and you've decided, what you've done is you're now writing down a theory of arbitrary numbers of particles, where those arbitrary numbers of particles, interact the way you would expect a charged particle to interact with the electromagnetic field. So we'll see how that works out in a minute, but that's the idea. But it's true that in general, when you do this, you're not, unless you can find unless you. Well, anyway, when you write these things down, they're no longer translation invariant or rotationally invariant. I mean, you can try and find some special configuration which has some kind of translation invariance or rotational invariance, but in general, you've broken all the Poincare symmetries by doing this.
So you mean the electromagnetic field already make the Poincare group useless? Right?
Already make what?
So it already made the electromagnetic field already makes the Poincare group like translation and rotation useless, right? Yeah,
so they're no longer. I mean, for a fixed value of this, you don't. It's not no longer a symmetry of the theory. Okay. So the state. So all of your states, you still have a perfectly decent notion. So maybe the thing to say is that you have a perfectly decent notion of what I call H1. So you have a notion of what are the solutions to the Klein-Gordon equation, in this background. If I write down the Klein-Gordon equation and I use covariant derivatives for it, then I've got it's a linear equation. It's kind of a nasty linear equation because it depends on this. It can be arbitrarily complicated to solve depending on this A, but I can, it still has all the same properties. It's a linear equation. This is a linear space. I can quantize it the usual way. But the problem is that since I lose, so here it's not just uncoupled oscillators. Yeah. The problem with losing.
Sorry, go ahead.
Yeah. But anyway, so the problem with losing Poincare invariance is that I've lost this nice property that I can write down the solutions explicitly, and I can quantize as a bunch of decoupled, oscillators, one for each p. But now, because things are not translation invariant, it doesn't. You can't write it as uncoupled oscillators in the same way.
So I guess when you write down the Klein-Gordon equation with the usual derivatives, you're already choosing Poincare symmetry, and here you're choosing to give that up for this gauge symmetry instead. Is that right?
Right. Yeah. That's in some sense right. Yeah. So I'm going to later recover. I mean, okay. In some sense, what I'm going to do later what I should say is I'm going to try to recover Poincare invariance by by quantizing this background field. So I'm gonna anyway. We'll talk about that next time. But right now you should think of this as this is a classical background that I'm putting my multi-particle quantum theory on, and it's just a bunch of charged particles running around interacting with this background, and it's doing what it does. It's actually, if you write down some arbitrary mu of x, it's actually very, very hard to solve exactly because you can't just kind of Fourier analyze and decouple everything. But in principle you can do it. Also, there are some actually very funny things that happen in this story if you get into it and try and think about it. And one of the trickier things that happens is that this guy, as you change your choice of a mu of x, you actually change what's positive energy and what's negative energy. So this decomposition of the field into annihilation creation operators and positive negative energy, if you do it for one fixed a mu, then as you vary the background field, it'll change. And so this is going to correspond to interesting physical phenomena, like kind of pair production of particles in a strong background electromagnetic field. So you have so you actually lose your kind of notion of nice distinction between here's my particle degrees of freedom and here's my anti-particle degrees of freedom. It kind of depends upon your choice of the background, and as you move the background, funny things happen. So it's a very what we've written down in some sense is a very non-trivial theory, and I can't kind of write down and I can't explicitly solve it except for some very special choices of a mu. But later what we're going to do is we're going to quantize the a mu degrees of freedom also. So and not keep them fixed, but kind of look in some sense look for solutions to the coupled to coupled field equations for the a's and for the phi's. And anyway, that's where we'll ultimately end up. And those coupled equations actually do have Poincare invariance, and you'll recover Poincare invariance then. But at this point, you've given up Poincare invariance. Okay, so now, the funny thing about the a mu's is that they, when you do a gauge transformation, they change. So they're kind of, your physics isn't supposed to depend upon, your physical states are supposed to be invariant when you do a gauge transformation. So these are kind of weird variables to be thinking about because they're in some sense kind of unphysical in that they change as you do gauge transformation. So what you want to do is you want to kind of you want to extract some information from these guys, which is the gauge invariant, which is kind of the gauge invariant piece of what this thing is telling you. And this is what this is in some sense the story of the electric and magnetic field. So let's do that. Okay, so let me define this way. So the gauge invariant info in the vector potential, in some sense, what you want to do is you want to define what you do is you take, it turns out that if you take this operator, which depends upon A, and then look at commutators with itself. So this will depend upon, there's some mu saying you're differentiating in some direction, you're differentiating in another direction. If mu is equal to nu, so this is just the usual commutator. This is you do this first, then this, and then you subtract where you do this first, and then this. And if mu is equal to nu, this is zero. But in general, and if A is equal to zero, then this is equal to zero because it's just the the fact that when you do two different derivatives in different directions, doesn't matter which order you do them in. But the order does matter if you have a non-zero A. And so we're gonna call this guy. I'm gonna call this guy. Give this guy a name. I'll also put an I and an E here, so to make this real. And so then you know. Okay. So this is anti-symmetric. In mu. So if you like to think in terms of tensors, these are, these are funny objects. They're not actually behaving quite like tensors, because they're doing something funny under rotations and translations. But anyway, this guy is a legitimate tensor. He's got two indices, mu and nu, that go from 0 to 3, and he's an antisymmetric. So this is an antisymmetric two tensor. Anyway, but it's also but the name is also given it. This is called the to physicists. So mathematicians. This is going to be called the curvature of the connection A, and the physics. This is going to be the field strength. So just kind of mathematicians and physicists terminology that if A is a connection, and when you write, then you take the commutator of the covariant derivatives, you call that the curvature, and we'll explain. Well, maybe I may explain a little bit about why. Or if you're doing physics, you say, well, you've got a vector potential, and you compute this guy, you get something called the field strength. Okay, and then more explicitly, what happens if you actually compute this and you use the fact that that the A's commute and you have the equality of mixed partial derivatives, what you end up with is this expression after you knew, which maybe is a simpler one that you'll often see people defining it this way, is that the A nu dx mu A u. Okay. So sometimes you'll see the definition just given this way, but it's the same thing. And maybe just to give things away, one reason that I wanted to define it this way is that we're going to be interested in what happens if you take the if you generalize from the group U of 1 to a larger non-commutative Lie group, and then what's going to happen is that this definition won't work, but this definition will. That's the motivation. And then this should be something, if you've had any kind of electromagnetism class, this should all start to look very familiar. And then what you do is you just define EJ0 to be the FJ0, and that's D minus DA JVT plus DA0 DXJ and B let me I guess I'll say it this way. So BJ is then epsilon JK AL of DAL DXJ, or maybe better to write it in vector notation, E vector minus BA vector DT plus grad A0, and B vector is equal to okay, so this is the standard thing that you'll see in any electromagnetism class, that you can how to go between a vector potential describing an electromagnetic field, and then an electric field and a magnetic field. And the point is that you can. The point of doing things this way is that you can you find that these are gauge invariant. So E vector and B vector don't depend are gauge invariant. Okay, so the problem with trying to work with A is that it's doing something complicated and funny when you act with this group on it. But if you act with the when you act with a group, these guys. So these are just functions of space time, and they have the physical interpretation that these are your that anyway. This is the electric field, and this is the magnetic field. Okay, so now what I want to do is let me kind of quickly show you that if we go back and look at all the equations that I had that I told you about for free particles from the beginning, from even the non-relativistic case, the Klein-Gordon case. If I go back and change derivatives to covariant derivatives, I'll get a new equation, and it's gonna, and we'll write it down, and you'll see what it is, and it's the equation that tells you how that quantum particle, how it behaves coupled to a background gauge field, to a background electromagnetic field. So let's just do that. Let me just do that quickly. Okay. Let's do the so for the non-relativistic particle. Okay, so what we do is we just take I d dt, but now so the time derivative now picks up. It's supposed to become a covariant derivative, so we have to put in this guy, A0 psi, and then it's minus 1/2m times the p squared operator, which is the derivative squared operator, but that's this guy. Okay. So anyway, so this is the Schrödinger equation. Or equation for a background, for a particle coupled to a background coupled to a background field. And maybe an example. One example would be that if you take the Coulomb potential, that would be A0 is 1/r, and B a vector, and the vector potential part is 0. Okay, so if you look at what happens here, what you end up with, you see that this doesn't change at all. All that changes is that you pick up an extra 1/r term. So this just gives you a 1/. This is just the problem of a particle in a 1/r Coulomb potential that we use to talk about the hydrogen atom. And this is really just so you can think about very often people teach the theory by writing down the Schrödinger equation for an arbitrary potential, but and then you solve for various potentials. But the interesting potentials are pretty much always going to be things like this that can be thought of as a background electromagnetic field that you've put the thing in. Okay. And then the other another example, which this one I won't write down, is that the constant magnetic field you can write down what happens if you choose A0 is 0 and B vector, no, A vector is minus B times 1. The X component is B times Y, and the rest components are 0. And anyway, if you figure out what this is, you'll find that, if you take the curl of this guy, you get a constant field in the z direction, and that's going to be so this is going to correspond to a electric field 0, magnetic field is just constant in one direction, and then you can I think that it might even be if you look at what this potential is you get here, what equation you get here. If you write this down, you'll find that it is something you can exactly solve. And I think it may have even been one of the problems in the first semester. Okay, but then the next thing to say maybe is is this well, actually maybe let's do the Klein-Gordon case. So it's easy. You just again you just write down minus ddt minus IE A0. So that you have a ddt squared term, and then you have the ddx terms. Well, it's got to be a sum. AJ minus m squared. Anyway, so this is the Klein-Gordon equation for. So this is if you want to think about the physics of scalars coupled to a background electromagnetic field. This is the equation you would solve. And if you take the kind of non-relative, if you take the non-relativistic limit, you should anyway in the non-relativistic limit you'll recover this guy. Okay. Then maybe one last thing to finish up is to start thinking about what happens for spin 1/2 particles. The spin 1/2 particles. And remember, so that not non-relativistically. So what I did was showed you that you could write down this thing I call the Pauli-Schrödinger equation by using the and it was a little bit silly because it didn't actually, it really just was an equation, 2 decoupled copies of the standard free particle Schrödinger equation. It had this nice feature that the Hamiltonian was actually a perfect square, but other than that it was but this becomes more interesting now. So what you do is, so this is Pauli-Schrödinger. What you do is you take I ddt okay, and so your psi is now psi 1, psi 2. Okay. And then you have your minus 1 over 2m p squared term, but the Pauli-Schrödinger idea was to write p squared as sigma in terms of sigma matrices as sigma dot p squared. So you're taking sigma vector and you're dotting it with what was your momentum. So it's going to be with the derivative. So it's a grad minus IE a vector. And then you're, and then this guy you're squaring and acting on psi 1. So if the big A's are 0, this is just the Pauli-Schrodinger equation, and it's just 2 copies of the standard Schrodinger equation. But in this case, it gets more interesting, and so I want to anyway. So I won't work out this equation. So you can use, maybe you want to say that this is so you use properties of Pauli matrices. So you have to use the commutation and anti-commutation relations for Pauli matrices, but then you can show that that sigma dot squared. What it is, it's the sum xj minus IEAJ. So it's it's the thing which is diagonal in these two components, which you expect, but there's also an extra term. Okay. So anyway, so what happens? So what happens here is that you've got, well, the time component of the vector potential just kind of changed. As usual, it anyway, it just shows up here. It just shows up here, and then the spatial components just show up again in the usual way, the same way that I wrote down for a scalar for a spin 0 solution of the Schrodinger equation or for the Klein-Gordon equation. But then there's this funny extra term that you get, because when you square this thing, it anyway if you do the calculation, you see that you get this, and so this is just the coupling. To a magnetic field. And so again, this was something that I started introduce very, very early on in this course, that if you wanted to just think about a qubit, if you wanted to think about a fixed particle at a point which couldn't move. So anyway, if you think about a spin 1/2 particle, it can move around, and the way it moves, its interaction with the electromagnetic field is just the same here and here, is just the same as what you expect for a anyway, for a single scalar particle, but the spin 1/2 nature shows up with this new. You get this new term, which is this coupling of the spin dotted with a B field, and I kind of use this as a motivation to talk about, like, if you talked about a particle that was infinitely massive, for instance, and then in the infinite mass limit, this behavior would go away, and the only thing you would have, the Hamiltonian would basically just be this guy. And so if you want to, so you can think about a spin 1/2 particle as having kind of the standard story going on, and as you move in space and time, but also kind of an extra thing going on, that the spin degree of freedom, couples to a B field in a way which is spatially independent, and you see it there. So this goes back to this kind of earliest, kind of simplest things I tried to write down about how to think about what a spin 1/2 degree of freedom is doing. Okay.
So does that term scale with m or something?
I guess, yeah. There should be, if I've written this down properly. Yeah, there's a 1/2m here. Yeah. So what I have to think about what happens if you solve this as a function of yes, but anyway, somehow, yeah. Anyway, what should morally happen after see how it happens is that as you take m goes to you can think of it. So this is p squared over m over 2m, and then this is and this is just a kind of a constant. Wait a minute, I'm sorry. Well, anyway, yeah. I shouldn't. I have to. I'm confused about how the M scaling works. But I'm just. But definitely, as you what should happen is that as you go to large M, this. Yeah. Anyway, you shouldn't. All of these states at with higher momentum go off to infinity, but these states should stay this should still be visible. Okay, maybe let me. I guess I better. Maybe it's a good time to stop there now. So I want to. Okay, actually, let me just tell you one thing. One more thing. Just in case you've seen this before. So if you've seen. You've seen so this whole formalism is kind of one of the great arguments for using the theory of differential forms. And I just want to say that if you've seen differential forms, what you want to do is you say that that A is the vector potential is a one form on M. And then there's this thing called the de Rham differential, which takes one form to two forms, and then F is equal to dA is a two form. Anyway, let me not and then you can integrate. Integrate along paths. And this thing you can integrate along on surfaces. So the whole idea of differential forms is that it gives you these, it tells you that these are things which are going to behave nicely geometrically in a way independent of which coordinates you choose. So I've written down these formulas for A and formulas for F, which depend upon my choice of coordinates. But if you want to be a real geometer and do things in a coordinate invariant way, there's a coordinate invariant way of thinking about vector potentials. It's something called a one form, and a coordinate invariant way of thinking about field strengths, which is, and then it's just dA, and the geometric interpretation of one forms is they're almost by definition things that if you take up the things which you can, they're kind of dual to paths. They're things which if you feed them a path, they'll give you a number. And these guys, these two forms are things which you feed them a surface, they give you a number. So this is kind of the beginning of the geometric interpretation. But I think what I'll do is I'll say a little bit more about this next time. And so next time I'll say a little bit more.
So can I somehow like rewrite the Klein-Gordon equation using some Laplace Bertrand operator?
Well, so the
like
yeah.
the summation of dxj minus iej squared, these things can you put them together to something like Laplace Bertrand?
Well, the thing about the Klein-Gordon equation is the equation for a scalar field. So, right. So phi is just a usual function. It's not. So there's no real reason to talk about. I mean, there is something you can do. You can write the Laplacian, but anyway, yeah. So if you're just talking about scalar fields, there's no good reason to use differential forms, right? So this differential forms business is useful for vector potentials and field strengths because they have this, they have this vector index and this two vector index, and they have this geometrical interpretation that you can integrate along paths, and you can integrate along. But I don't know, but in a Klein-Gordon equation, it's for a scalar field. The scalar field is just a function. There isn't much of a role for the theory of differential forms there. Okay, that help. Anyway, and then so let me say a little bit more about the geometry associated with these, and then the next thing to say is about U1. We'll try to take U1 and turn it and this U1 gauge symmetry and turn it into a more interesting symmetry, and this is called the Yang-Mills theory. So you get a generalization of electromagnetism called the Yang-Mills theory, and we'll talk about that. And then the next thing was go on to quantize as the A field, and we're going to get we use Maxwell's equations, and this is a somewhat long story, which we'll talk about it, and this will end up giving you the theory of photons. But those are the kind of the remaining parts of the story I want to tell you about vector potentials and about field strengths. Are there any questions about any of this? Actually, have any of you seen differential forms? Have you seen it? It's kind of a, yeah, it's mathematically it's somewhat of a strange subject. It's a little bit hard to understand how, like, why this mysterious D is. But I think one of the kind of the great motivations actually for the mathematics and for that kind of geometry is exactly this theory that if you write down A and F in terms of differential forms, the formulas all become kind of trivial. Okay, well, if there's nothing else, then I guess I'll stop this. But again, I'll be around for a while. Please do come back. Bye for now.
Thank you.